In this video, we will be looking at linear combinations and spanning sets. So to start, let's remember that when you add two vectors, or you add the scalar multiples of two vectors, like this, a times vector u plus b times vector v, you get a new vector, and this is called a linear combination. So where have we seen these linear combinations before? We know that we can write a position vector, let's focus on 2D for now, as AB. But we can also write it as a linear combination of the unit vectors. So A times unit vector I plus B times unit vector J. That is a linear combination. And because I can write any vector in 2D as a linear combination of these two unit vectors, we say that the unit vectors I and j span that two-dimensional space. So they span R2. In general, a set of two vectors form a basis or a spanning set for R2 if every vector in R2 can be written as a linear combination of these two vectors. So I and j form this basis or the spanning set because any vector can be written in terms of I and j. Now, the only time two vectors in 2D will not form a spanning set is if the two vectors are collinear. So I'll make a little note of that. Collinear vectors cannot form a basis or a spanning set for R2. So let's look at a few examples in 2 dimensions. So we have a set of vectors. Vector u is 1, 1, and vector v is 1, 2. Show that this new vector w can be expressed as a linear combination of u and v. So our goal is to write w as something times vector u plus something times vector v. And I'm not going to sit here guessing and checking values of a and b. So let's see what we can do. Here's vector w. Here's vector u and vector v. Now I'm going to pull out all of the x components. So the -2, a times 1, and b times 1. So -2 should be written as 1a or a plus 1b or b. Now I'll do the same thing for the y components. -7 can be written as 1a plus 2b. And now I have a linear system. Now we're in grade 10. I need to solve for a and b, and I have two equations about a and b. Now the coefficients of a already match, so I'm just going to subtract my lines. -2 minus -7 is 5, a minus a is 0, b minus 2b is -b. And if I divide both sides by -1, I get that the scalar multiple in front of vector v should be -5. And now I can take this and I'm just going to plug it into my first equation. So -2 equals a minus 5. Bring that -5 over, so -2 plus 5 is 3. So those are the scalar multiples that we will need. So now I can write vector w as 3 times vector u minus 5 times vector v. And because I was able to actually create this linear combination, I know that u and v do form a spanning set for R2. I can also verify that by looking at these vectors and saying, hey, they are not collinear. So for part B, that's exactly what we're going to do. Show that vector u and vector v form a spanning set for R2. Now, we did just show it with this specific example, but we can also repeat this process for a general vector. So let's say my general vector is xy. If I can show that any vector xy can be written as a times vector u plus b times vector v, then that is one way for me to prove this idea that u and v form a spanning set. So let's see what this is going to look like. X equals a times 1 plus b times 1, and then y equals a times 1, b times 2. Okay, the a's have the same coefficient, so again, I'm going to subtract. X minus y equals a minus a is 0, b minus 2b. There we are. And I end up with the fact that negative x plus y is equal to b. And then if I sub that in, I can figure out what a is equal to as well, just like I did in the previous example. So x equals a, and then for b, I'm going to put negative x plus y, and I'll just bring those over. So x plus x minus y equals a. The fact that I was able to find an expression for a and b means that I can write any vector xy in terms of vectors u and v. So therefore, any vector can be written as a linear combination of u and v. Therefore, they form a spanning set. Now, that is the longer way to prove this. Another way is to prove that these vectors are not collinear. So I have to show that 1, 1 cannot be written as k times 1, 2. So let's see. Can I show this? If I look at the x components, 1 equals 1k, so k equals 1. But if I look at the y components, I get 1 equals 2k, so k equals a half. These are inconsistent. So there is no value of k to make one vector equal the other, a scalar multiple of the other, so these are not collinear. Therefore, u and v are not collinear, so therefore they form a spanning set in R2. Obviously, this is the faster way to do it, but we have two methods. Now, for the next example, show that 1, 1 and 2, 2 does not span R2. So this set of vectors does not span R2. Well, just looking at this, we know that these vectors are collinear. 2 times the first vector equals the second vector. Therefore, these vectors are collinear. Therefore, they do not span R2. In general, any pair of non-zero, non-collinear vectors will span R2. Now, let's take this and put it in 3 dimensions now. We've seen linear combinations in 3D as well, because we were able to write any vector, let's say vector ABC, we can write it as a linear combination of vector I, vector J, and vector K. So those 3 vectors form a spanning set for this 3-dimensional space. So what does the span of only two vectors in R3 look like? What space is produced by all the linear combinations of only two non-collinear vectors in R3? Okay, let's just start with a little diagram. So here's the z-axis, the y-axis, and coming forward is the x-axis. There's the negative part of each axis. Now, if we only had two vectors, well, if you have two vectors, imagine you're holding two pencils. Those are just going to form a plane in three-dimensional space. I can't form every single vector out of just two. Out of two vectors, I can form any vector on a specific plane. So let's say the vectors I drew are on this plane here. So I can combine those two vectors and form anything on that sheet, that three-dimensional sheet of paper, of space, whatever you want to see it as, but I cannot form any other vector. So any pair of non-zero, non-collinear vectors span a plane in R3, so in 3D. Such vectors are said to be coplanar. So if I want to find a linear combination of a vector in a specific plane, I only need two. If I want to write any vector in 3D as a linear combination, I need three vectors, and those three vectors would create that spanning set or that basis in 3D. So let's show that the vectors 2, 1, 1, -1, 1, 3, and 7, -1, -7 are coplanar and therefore do not form a spanning set. Now, in order for us to do this, if we can show that one vector can be written as the linear combination of the other two, then these three vectors must be coplanar. They must exist in the same plane. So let's just pick a random set. I'm going to try to write this vector here as a combination of the other two. So 7, -1, -7 is going to equal, maybe, we don't know, A times the first vector plus B times the second vector. And this is going to be the exact same as the previous example, except now we have three components, but it's still only two unknowns. So we have 7 equals 2 times A minus B. And then for the y component, -1 equals A times 1 plus B times 1. And then -7 for the z component equals A times 1 plus 3 times B. Now, I really only need two equations to solve a linear system. So I'm just going to use these two equations, and this third one, I'm just going to use it for a check. So I'm going to rewrite the other ones. And the b's both have a coefficient of plus or minus 1. So I'm going to eliminate them with addition. And of course, I've been doing elimination here, but you can of course use substitution to solve the linear system. So we have 6 equals 3a, and if we divide both sides by 3, a equals 2. I'm going to sub that back into one of my equations, and when I bring the 2 over, I get -3 for b. Now that's great and everything, but let's make sure it works on that third equation that we haven't touched. So I'm going to do a little left side, right side check. The left side of the equal sign is -7. The right side is a plus 3b. So -7, I can't do anything with it, but for a, I'll put 2. For b, -3. That's 2 minus 9, which is -7. So the fact that I was able to write one vector as a linear combination of the other must mean that these three vectors are coplanar. Therefore, these vectors are coplanar since one can be written as a linear combination of the other two. Now I just chose this randomly, but I could have done any combination. Like I could have written the first vector as a linear combination of the other two. In general, any three non-zero, non-coplanar vectors form a basis for R3. So these do not form a basis or a spanning set for R3 because we could write one in terms of the other two. They're in the same plane. And that's it for our linear combinations and spanning sets.